Alright, greetings everyone. Here are some more examples from the Chapter 2 review section, exercises section of our textbook. I wanted to go over three of the limit problems early on in the find the limit sections in numbers 3 through 18. Two of them look very similar to each other, but the results and how we evaluate them are different. This is number 4. As you can see, we have the limit as x approaches 3 of the quantity x squared minus 9 divided by the quantity x squared plus 2x minus 3. Okay, we'll talk about the solution of that in a moment, but look at the structure for a second. And then if I go over to number 5, so now the limit as x approaches negative 3 of x squared minus the quantity x squared minus 9 divided by the quantity x squared plus 2x minus 3. So we're evaluating the same function in both cases, or the same expression in both cases, but we're letting x approach two different values. In number 4, x is approaching positive 3, and in number 5, x is approaching negative 3. So let's see how these in fact are different. Well, as I've mentioned in class, the first thing that we want to do to check to see if the limit exists is to do direct substitution. So if we can directly substitute 3 into this expression and get a real result, then that'll be our limit. And so now if I plug 3 into the numerator, I'm going to get 3 squared, which is 9, minus 9, and I get 0. 0 in the numerator by itself is not a problem. It all depends on what's happening in the denominator. So if I plug in 3 into the denominator, we get 3 squared, which is 9, plus 2 times 3, or plus 6. 9 plus 6, of course, is 15, and minus 3 is 12. So this is easily evaluated just through direct substitution. This becomes 0 divided by 12, and then we know anything that's 0 divided by any non-zero number is going to be 0. Alright, so that's by direct substitution. Direct substitution. Alright, let's go on to number 5 here and see what happens. Now I have x equals negative 3. And if I plug x equals negative 3 into the numerator, we get the same result, because negative 3 squared is 9, so 9 minus 9 is still 0. When I plug negative 3 into the denominator, I don't get the same 12 that I got before. Although when I square it again, I get positive 9 here. I'm going to end up now adding a negative 6. 2 times negative 3 is negative 6, so we'll have a 9 minus 6, which is 3, minus 3. So this is approaching 0 over 0. This is one of our indeterminate forms. Okay, this means we have to investigate further. We cannot get a result from 0 over 0. Sometimes when we get 0 over 0, we get a limit that exists. Sometimes when we get 0 over 0, we get a limit that does not exist. And so this by itself doesn't tell us anything. So the first method that we want to try to do now, since direct substitution failed, is to use some algebra to the expression to see if there's a way of reducing or rewriting the expression that is in equivalent form around negative 3 that will accept negative 3 as an input. So you've probably already noticed, you may have already worked it out for yourself, that we could factor the numerator and factor the denominator. Remember, I need to keep putting the limit down every time I rewrite the expression when I haven't evaluated the limit. So factoring, we're going to get an x plus 3 times x minus 3 in the numerator. And then in the denominator, we're going to get, I should have factored this ahead of time in my mind, but it's not too hard. You can see the result is x plus 3 times x minus 1. Alright, now we notice that we have the same factor in the numerator that we have in the denominator. And since we have the same factor in the numerator and denominator, we can cancel these factors because the limit doesn't care that we have the denominator 0 at negative 3 for that term. Because, again, the limit isn't really looking at x equals 3. The limit is looking at the function as x approaches negative 3. So canceling this out is legitimate in this case. So now we're left with the limit as x approaches negative 3 of x minus 3 divided by x minus 1. And then we can do direct substitution into those quantities, and we end up with negative 3 minus 3, which is negative 6, divided by negative 3 minus 1, which is negative 4. and then that's going to reduce to just a positive 3/2. So we see that although we had the same expression, we had to use two different techniques. In example number, or problem number 4, we could use direct substitution and get a result that was meaningful, and in number 5, direct substitution failed, so that we had to rewrite the expression using algebra and try to find a better method to evaluate it. One more example. Let's take a look at example number 9. This is the limit as r approaches 9 of the square root of r divided by the quantity r minus 9 to the 4th power. Again, if we look to directly substitute here, we do have a problem, but not the same problem that we had in number 5. When I plug in 9 into the numerator, we get the positive root of 9, which is 3. Remember, there's no plus or minus here because there was no plus or minus in front of the square root. The definition of the square root symbol is the positive, or the non-negative root. To be more proper about that, the non-negative root of the input, which is the input in this case is 9, so 3 is our result. Divided by, well, if I substitute 9 into the denominator here, we get 0. Okay. And we know that we don't want to get anything, we don't want division by 0, so this is something that we don't want. It was supposed to be a complete circle. Excuse that little part right there. But although we don't want it, that doesn't mean we don't get something from it, okay? Because this is not in the indeterminate form 0 over 0, we still have some meaning happening here, okay? What's going on here is the denominator is getting smaller and smaller and smaller as r gets closer to 9. This part here is approaching 0. The numerator is approaching the constant 3. So if you think about the examples that we've done before where the numerator is approaching a constant but the denominator is getting smaller, the quotient is going to be getting larger. Okay? You know, for instance, if we divided 3 by 1, we would get 3, of course. If I let the denominator get get smaller, 3 divided by 0.1, then we get 30. If I let the denominator get even smaller by 0.01, or dividing 3 by 0.01, then we get 300. And that pattern would continue. If I allow the denominator to keep getting smaller, the outputs would keep getting bigger. So this would seem to tell us that the outputs are going to approach infinity. Now we do have to be careful here because we are dealing with a possibility that from the left and the right we don't have the same infinity for which the function is approaching. But nonetheless, we do know that the quantities in magnitude are going to be getting larger. Now this 4 that we have here in the exponent for the denominator is going to be a factor of the answer, or is going to affect the answer. I shouldn't use a math term like factor there, but it's going to affect the answer because this is an even power. And so no matter what values I plug in for r, approaching 9 from the left or the right, the quantity inside this expression, inside the parentheses here, is going to be raised to an even power. Well, and will always come out to be a positive number. And therefore, we're always going to have a positive 3 divided by a positive number. So from both sides, the limit's going to approach positive infinity. And I'm just going to write that down here, just so that I'm clear. So the limit as x approaches 9, and that should not be an x. Sorry about that. Let's fix that really quickly. It should be as r approaches 9. The limit as r approaches 9 of this, from the left, of the square root of r divided by r minus 9 to the 4th power. Again, as I've already argued, this is going to approach positive infinity because of the even exponent in the denominator. And then the limit as r approaches 9 from the right of this root r divided by r minus 9 to the 4th, again, is going to go to positive infinity. Let's make sure that argument is a little bit more complete for you so you understand this explanation. As r approaches 9 from the left, that means r is taking on values that are less than 9. So I'm going to have some number less than 9 minus 9, which results in a negative quantity. But again, the negative quantity is going to be raised to an even power, to the fourth power, and therefore will result in a positive number. And so the positive numerator divided by the positive denominator gives us a positive quotient always, but the magnitudes are getting bigger, so the result of the limit is to approach positive infinity. Similarly, for r approaching 9 from the right, now r is going to take on values that are bigger than 9, so r minus 9 is going to be a positive number raised to an even power, which remains positive. And so we'll have, again, a positive numerator divided by a positive denominator, which results in a positive quotient. And so the magnitudes are going to get bigger and stay positive. So the limit is going to, from the right, is going to approach positive infinity as well. Now remember, we can summarize this by combining them into one single limit. And all of a sudden, now I want to use a cursive L. I don't know why. The limit as r approaches 9 of the square root of r divided by r minus 9 to the fourth power, then is just going to equal positive infinity. Because from the left and the right, we get the same infinity. Now remember, one last reminder here, that just because we write equals infinity does not imply the limit exists. In fact, we know infinity is not a number, so we are saying here that the limit does not exist, but we are telling the reader of the solution that the trend of this expression, as r is getting closer to 9, is from both the left and the right, that the magnitudes of the outputs are growing without doubt, are heading off towards positive infinity. So that's what we agree upon that this set of symbols represents. Okay, so go study and go practice.